Master's in Biochemistry and Molecular Biology, again at UBC in 1993. He taught at the colleges of the Bahamas, nice, and Langara College in Vancouver, and has been a faculty member of the biology department at Vancouver Island University for 21 years. Rob became interested in GMOs after reading Pandora's Picnic Basket in 2000. It was clear the internet was full of false information on the subject, so began writing articles and giving public seminars to help explain the real science of GMOs. He's written dozens of articles and given radio and TV interviews and given many public talks. Many can be viewed on his website, robwager.com. In recent years has political decision makers becoming interested in GMOs. He has written to and spoken with local, provincial, and federal politicians who wanted accurate information on GMOs. Rob spends considerable time on internet forums and blogs, challenging the fear stories critics of GE technology continually push. Robert received the 2013 Crop Life Grassroots Award for his efforts helping educating the public about GMOs. Fear does sell, but Robert has found well-researched and calmly presented. So, now let's hear Rob tell us how we're going to feed 10 billion people. Please help me welcome.
Thank you. As mentioned, I started in this area about 2000. Food's a very visceral subject. People have emotional attachments to their food, and fear is one of those emotions. A lot of the public have genuine fear about this subject. The fear is real. The reasons for that fear are not. And so I'll try and challenge some of those myths today about genetically engineered crops. And first off, it should be clear that I have not, and I do not, receive any money from the biotech industry, nor does my institute. So I am just a third-party scientist who talks about the science to the public. So for most of human existence, we were hunter-gatherers. But about 10,000 years ago, that changed when we began something called agriculture. And for most of that 10,000 years, we used primitive tools, primitive irrigation, and saved what back then were naturally derived seeds. Each year we would save the seeds, and small changes in the DNA happened from year to year. And so over long periods of time, centuries or millennia, those small changes in the DNA of the seeds of our food became large changes of DNA. One of the good examples is brassica, a wild weed. About 500 BC, we changed the DNA and got kale. By changing the DNA of kale, we got cabbage and kohlrabi. By changing the DNA of cabbage, we got the cauliflower. By changing the DNA of cauliflower, we got broccoli. Then, unfortunately, they slipped up a bit. Here it comes. Come on there. They created Brussels sprouts. Sorry about that, I wasn't around to maybe steer them a different direction. But as you can see, there's very large differences in all these crops, and they all came from a wild weed. The large differences are because of large changes in the DNA. This is what the wild relatives of our food look like. They don't bear much resemblance to the food we take for granted today, and the reason being we've changed the DNA over the millennia. Corn's a really good example. This little thing here is called teosinte. It still lives, or still exists, in areas of Central America, particularly in southern Mexico. But by changing genes of this, over a very short period of time, about 8,000 or 9,000 years ago, we got to this variety of corn, and then recently we've changed the DNA some more to get to the modern variety of corn. If you look at this cartoon here, this picture up here represents the genomic structure, the whole DNA of ancestral rice. So everywhere you see a yellow line, we used either radiation or chemicals to cause random mutations in the DNA. Everywhere you see a pink line, we added DNA in from another species. everywhere you see a dark blue line, we moved large chunks of the DNA to different parts in the genome so that they are regulated at a much different level. Everywhere you see a light blue line, huge chunks of DNA have been taken out, just gone. So you can see the modern variety of IR64, which is the most commonly grown rice variety in the world, has very little different, or very little similarities to the genetic structure of its ancestor. All of this DNA change, nobody bats an eye. Add 3 genes, over here, we get something called golden rice. It's been in the regulatory purgatory for the last decade. We'll talk more about that a little later. You often hear people say that GM crops are brought to market without any testing. That's simply not true. On the right are all the tests in that folder that have to be done for a non-transgenic variety of flax to be sold commercially in the US and Canada. They added 1 herbicide tolerance gene to that variety of flax. On the left are all the tests that had to have been done in order to commercialize that now transgenic GMO variety of flax in Canada. That didn't even allow it to be sold across the border in the United States. We test extensively. On average, it takes between 8 and 13 years of testing and tens to hundreds of millions of dollars in order to get a new genetically modified crop commercialized or allowed to be what's called deregulated. We test a variety of things for nutrition. We also test a variety of environmental considerations. In fact, this one from the USDA shows 28,000 different field tests that have been carried out on GE crops before they were allowed to be commercialized. So the next time somebody says to you that GM crops are brought to market without testing, remember this picture. In our lifetime, agriculture has gone through tremendous changes. We have increased the yields by 250%. That's with almost no difference in the inputs. One word describes how we got there: technology. I'd like to paraphrase Carl Sagan. He said that most parts of society depend on science and technology. Unfortunately, most people do not understand science and technology. This is a recipe for disaster, and I would argue that we're there now. There's always been opposition to technology, and there is a very fierce opposition to genetically engineered crop technology. In fact, it's a multi-billion-dollar multinational group of people who would like to convince you that GE crops are dangerous or harmful to the environment. They rely on the public's ignorance about food production. The vast majority of the population, 98%, do not have any direct connection with primary food production and haven't had connections often for generations. It is easy to use fear stories to convince people of things that simply aren't true. They love to use pictures like this. If you see an article that has this kind of a picture where a syringe is sticking out of a piece of food, you can almost invariably count to be misled by the content of that article. We do not use this type of technology to move DNA around. If you go on the internet, you'll type in GMO poison. See how many hits you get in 1 second. This was a couple of years old, over 2 million hits for GMO poisons. The reality, after 6 trillion meals, there's not a single documented case of harm from people consuming food with ingredients derived from GM crops. Most critics are not farmers. They live in offices in Brussels, San Francisco, London, New York. It's easy to be a critic when your plow's a pencil. This is what a GM crop looks like. We have corn, we have soybean. They look exactly like non-GM counterparts. Canola. If you go on the prairies, you'll see in the midsummer huge, huge acres of yellow fields, and that's all canola. Now there are two main traits that are primarily responsible for most GM crops that are grown today. The first is herbicide tolerance. Weeds will sap yields faster than almost anything. They take the moisture, they take the nutrients. So farmers have had to deal with weeds since agriculture began. We've used a variety of methods, whether it be mechanical, plowing up the weeds, or chemical. So they've always had to deal with this. We introduced a herbicide tolerance gene into GE crops. The tolerance is for a compound called glyphosate, or most people know it as its trade name, Roundup. Glyphosate targets an enzyme system that's only found in plants. So it's very non-toxic or minimal toxicity to anything other than the plants that it comes in contact with. Animals don't have any effect, virtually no effect, at the concentrations where it's used. You can see why farmers have adopted this technology though. They can plant their seeds and allow them to grow up a few inches, at the same time they allow the weeds to grow up a few inches. Then they spray the whole field with glyphosate, only the weeds die and their seed crops grow up fine. It's true that herbicide tolerance traits have resulted in an increased use of Roundup or glyphosate. But what most people don't realize is that it's because glyphosate has replaced a whole slew of other herbicides that were used by farmers prior to the invention of herbicide-tolerant crops. And if you compare the environmental impact of these herbicides versus glyphosate, it's a huge benefit to the environment to switch to this relatively non-toxic compound called glyphosate. And by the way, the patent ran out long ago, so Monsanto no longer owns the patent on Roundup. On Roundup they do as a trade name, but not on glyphosate. It's made by many different companies. In fact, most of it is made in China nowadays. I like this quote. It talks about the other main trait that is involved in the first generation of genetically engineered crops. An extraordinary variety of alternatives to chemical control of insects. Many are little more than ideas in the minds of scientists, and many are waiting the opportunities to be put to the test. They all have in common understanding of the biological agents, in this case, insect pests, we're trying to control. Anybody have an idea who that might be? Who said that? Rachel Carson, Silent Spring, 1962. So even back then, she understood a little bit of the power of this science. Now, insect-resistant crops have allowed farmers to dramatically reduce the amount of broad-spectrum insecticides that they use in field crops. Hundreds of millions of pounds each year are not applied to crops because the crops protect themselves. Along with the insect pests, one of the things that is very common are fungal contaminations. So once the insect causes some damage to the food crop, it brings or opens up the opportunity for fungal pests. Fungus produce some of the most toxic compounds on the planet. And many people, particularly in the developing world, suffer from extreme fungal toxins because their food gets damaged by insect pests. It's easy to see why farmers have adopted this technology as well, where you can have a cotton field that gives a very good bounty. You didn't have to spray broad-spectrum insecticides. Over here is what would have happened without that one gene that was inserted into the crop. So you have to plant what are called refuges. So those are areas where insects can be exposed or have contact with the non-GM variety to hopefully reduce the development of resistance in the insect pests. This is mandatory in all GE crops. Along with fungal problems, insect pests often bring viral pathogens. So for you and I, we can get vaccinated against a variety of viral diseases, but plants can't. So what scientists developed were, by moving a single gene from the viral pest, in this case the papaya ring spot virus, into the papaya plant, then this is the same plant, one gene difference, grown in the presence of the viral pathogen. You get beautiful yields of the transgenic variety and complete decimation of the non-transgenic variety. And this is happening in Hawaii right now. Over 80% of all papaya that are grown in Hawaii have this one gene transferred from the viral pest. They're protected from the viral pathology. You often hear that GE crops are only there to make money for the big corporations that produce them. Actually, 17 million of the 18 million farmers who grow genetically engineered crops are in the developing world. And recently, the developing world passed the developed world in acres of GM crops that are planted now. Each year, over 450 million acres are planted to genetically engineered crops around the world. In the developing world, other stresses are becoming a real problem because that's where most of the population growth is occurring. And drought is one of those. Right now, drought tolerance corn is being field tested in Tanzania and a couple other countries, and it's showing dramatic results. So one of the abiotic stressors, so it's not an insect, it's not a virus, it's not a fungus, it's not a weed, but it's a weather. When you have no moisture or very little moisture, it's very hard to grow a crop. Viral pathogens, just like in the papaya, in this case, cassava. Over 500 million people rely on cassava for the most of their nutrition. It's a root crop, much like a potato, and it grows in very poor soils. So it's very productive in many parts of Africa. But it suffers from a viral pest. The same thing, by taking one gene from the viral pest, putting it into the plant, you now get a transgenic, genetically modified cassava that is completely immune to the viral infections. In India, or in this case, Pakistan, eggplant, or brinjal as they call it, is a staple crop. But it suffers from attacks of the root and shoot borer. So much so that Indian farmers and farmers in that general area often have to spray their crops over 100 times during a growing season, because you have to make contact with the insect pest while it's still on the outside of the eggplant. So almost every day they're spraying. And this is very often the case. No protective equipment whatsoever. Again, by moving a couple genes into the brinjal, we've got a situation where the plant protects itself from these insect pests. And we're seeing dramatic improvements. 100% reduction in, 85 to 100% reduction in insecticide use, and yields far in excess of what they could get if they were using insecticides before. So it's very popular in Bangladesh, and it's expanding dramatically. And India, the farmers are now calling for it. Now, even if the government says no, it's very likely we'll see the same thing that we saw in South America, where this technology will move across the border regardless of government sanctions in India. We saw the same thing with soy in South America when Argentina allowed it and Brazil did not. Very quickly, the farmers themselves moved that technology across the border. Another tremendous success that you don't hear about is flood-tolerant rice. In places like Bangladesh, often monsoon rains are very extreme, and the rice fields may flood for 2 or 3 weeks. Usually, that kills the vast majority of the rice. By putting in one gene, and this particular work was done at UC Davis in California, you get sub-1, and you can see on the left here is a variety of rice without the sub-1, and on the right, so in the same field, under the same conditions, and the same here. Without the gene, with the gene. One gene, tremendous yield differences. We're looking at 3 times the yield in rice. Presently, over 2 million farmers now grow this type of flood-tolerant rice in that area. I mentioned golden rice at the beginning. 800 million people suffer from vitamin A deficiency in the world. By adding 3 genes, 2 from bacteria and 1 from corn, we're able to produce physiologically significant levels of beta-carotene, to give it the yellow color, which our bodies then convert into vitamin A. This, by moving these genes, because it's a transgenic technology, it has been stuck in regulatory purgatory for over a decade. It's hoped that it will move forward in the next few years. We'll see. 800 million people could benefit from this.
Isn't that for blindness?
Yes. If you lack vitamin A, it also causes a variety of immunodeficiency diseases, and often the children or young people suffer the worst fate, which is death. Recently, a report out of Germany looked at 150 different publications and found on a global scale a 21% increase in yields, a 39% decrease in pesticide applications, and a 68% increase in profits for the farmers. Most of that profit at the high level is in the developing world, where they were getting very little yields before this technology. The second generation of GM crops are beginning to come on the market, and they have traits that directly benefit the consumer, not the producer. So we have things like non-browning potatoes and apples. So they take potato genes and put them into potatoes to control potato genes. We have apple genes put into the apples to control apple genes. And we have transgenic salmon, which has recently been released or deregulated by government agencies both in the US and Canada. So this fish grows almost twice as fast. So an environmental impact, you can grow twice as much protein by adding 1 gene. And it's a salmon gene that's put into the Atlantic salmon. It's controlled by a regulatory piece of DNA from an Arctic fish. The truth is, by 2050, we're going to have 9 to 10 billion people. We're going to need the best of every technology in agriculture. We're going to need the best of organic agriculture. We're going to need the best of agroforestry, the best of integrated pest management, the best of agroforestry, and we'll definitely need the best of genetically modified crop technology. Thank you for listening.
So who gains from all the fear-mongering about?
People who are selling you alternatives products, or the people who are soliciting funds for their organizations. So often environmental groups will use fear, and this is just one of their targets, to solicit funds. And there's a very significant contribution from alternative food and health products who are contributing billions to scare you, because that itself is a $100 billion industry. And so they want to keep that going.
So could you call it GMO? Oh, sorry.
Go ahead, you started.
Oh, I was just going to say, would a GMO product ever be considered organic?
I think that viral resistance or insect resistance are ideal products for the organic industry to adopt. In both cases, you get a tremendous reduction in the amount of broad-spectrum insecticides that have to be applied, and you get, what's really interesting is BT, which is a bacteria that produces a variety of proteins that are used in insect-resistant crops. BT is used in organic agriculture. So they use the whole live bacteria, but if you take up just the one gene that actually does the protecting and put it into a crop, all of a sudden it becomes wrong. So there's a debate within the organic industry that if our true goals are about environmental stewardship, then some of these things should be adopted. I don't think they'll ever adopt herbicide tolerance as a trait, but they should really look at it on a case-by-case basis. Yes?
One of the things you were talking about at the beginning of your presentation was the idea that humans change DNA. Is the implication that selective breeding which is how agriculture slowly changed. Was it actual us changing it, or what was I wasn't certain.
Well,
what
the
your
changes
wording.
were random,
Mhm.
but then we put selective pressure to fix them within the genome
Yeah, so we
population.
chose
Yeah.
those
So
random.
back then, we did not have, we just found that, well, this one grew a little better.
Yeah, and
So
then
we'll
we
take the
would- we would
seeds from
collect
that.
those
We never
seeds,
knew
exactly.
what changes happened,
Yeah, so we weren't physically changing it as
other
is being
than
done
putting
now.
selective pressure on, and
Yeah.
so the DNA changed over time.
So
Yes.
one of those changes, though, as we saw, was a huge amount of biodiversity that was occurring in terms of having a lot of different crops. And I know one of the concerns that I've read about, that I wonder about, is that I know, for example, in rice crops, because people selected in all types of different areas with different weather regimes and so forth, the strains of rice that you find in different areas really varied a lot, and they were selected for growing in that area.
Absolutely.
So there is that big biodiversity, part of which is saved in the seed banks that we have globally for the different key grain crops in particular. But the concern there is in going to the GMO crops, generally because of the high cost, as you saw, all the regulatory measures and so forth, how, we're gonna be only choosing one or two strains that have this ability. So how do we maintain that biodiversity that we do have, that's gonna give us backup with climate change and other pressures that are also part of what's coming in the future?
It's a good storyline, but it's not true. There's huge genetic diversity in crops. The idea that we have one or two or a half dozen crops, there are 60,000 different varieties of seeds available in North America right now. There's as many varieties of crops as there were 100 years ago. Now, it's true that some of those heirloom varieties have disappeared or are very hard to find, but the genetic diversity has been maintained by and large. It's interesting, I read something last week that said that genetic differences within corn varieties are equivalent to the genetic differences between humans and chimpanzees.
Well, it's interesting, because I know a lot of farmers, and I know people who are growing some very specific types of corn, which make the best corn on the cob. And they were growing this in the 70s and 80s. They can't find the seed for it anymore. Like, all that you can find, there's a couple of varieties. They're finding it really difficult at a commercial level to be finding that variety.
You're right, there is always pressures, but if there's not a demand, seed producers are not going to produce it.
Mhm.
So having a small market, although it's important to the small percentage of farmers who want that, you have to have economic considerations because it's very expensive to maintain a seed variety.
Mhm.
And so it's a give and take. In an ideal world, we'd be able to keep every kind of seed that ever existed. But we don't live in an ideal world.
There we go.
So people are aware of that, but the idea that monocultures are dramatically reducing biodiversity is more a myth than it is reality. It's something to be concerned about,
Mhm.
and people do pay attention to that. And there's, I think, about 8,000 different varieties of corn available. Most of those are land races that are grown in its ancestral place in Mexico area.
Yeah.
But the genetic diversity is maintained within those land races.
Well, is that because of the Seed Institute in Mexico City?
No, it's the farmers.
The
The
farmers
farmers
are still
themselves are
Because if you've
very
got
good.
farmers, then why would they go over to if they go over to genetically modified corn, which is only gonna be a few varieties based on, what's
Yield.
available?
Yield.
Yeah, but then what happens to those varieties that they have been growing?
It depends.
Would it depend on whether they're farming for subsistence or whether they're farming for?
Yes, that would definitely influence their decisions. Farmers in that part of the world are very good at maintaining genetic isolation between two fields that are even right side by side, so that they can maintain landrace isolation between two crops that are grown even side by side. They've practiced this for thousands of years, so it's not a big challenge for them.
So you said you had a website,
Yes,
and it's your name,
robertwager.com.
oh, okay.
Oh, Robert?
Yes.
Okay, I put down Rob Wager.
Yeah. Yes, sir.
So with the climate warming and sea level rise, I expect we'll probably lose a lot of arable land. are we really going to have a choice to not use GMOs versus the traditional way of selecting better crops?
No, we don't
Like,
really.
especially in poorer countries. We're a rich country, we can afford to outspend the poorer countries to get the food we want. Do you see that the poorer countries are going to adopt this much more quickly?
Oh, absolutely. We're seeing it right now. China has made it very clear that they're going to go full steam ahead with this. They're spending billions of dollars on R&D and a little bit of clandestine borrowing germplasm from the US from time to time. So they're very clear going this way. India will get there because the countries around that region are already starting to move that way. The Philippines, Vietnam, Malaysia, Bangladesh, there's about 7 countries in Africa. The developing world realizes the power of this technology, and they're developing it for themselves. So it's not big companies like Monsanto, which recently got bought out by Bayer, that are going to be the primary drivers. It's going to be in-house development by these countries. Over 70 countries in the world have active R&D programs on this technology for the crops and the specific problems they have to deal with in their areas.
And presumably for what they're foreseeing in the future as well. To your point.
Any other questions?
The viruses are changing and evolving themselves, aren't they?
Yes.
Does that mean that there's going to be a constant change in the change of these plants that are resistant to these viruses?
When a virus, what we usually pick for the target gene is the protein gene, the gene that codes for the protein on the outside of the virus. That protein has to be a specific way in order for it to attach to its target cell. So there are evolutionary constraints on the protein and therefore the gene that codes for the protein, so it can't change much. So those are the sections that you take, those that have selective pressure to maintain a certain structure. Now, everything changes a bit over time. And in fact, cassava was a really good example because the very first attempts at creating a viral-resistant cassava took the virus from a different area. And they took the gene from that and put it in. And so when they grew up the test plants, there was no viral resistance because the genes were a little bit different between the viral pests from the different areas. So you have to work within the local environment if you're going to do that technology, to take the local varieties of pests, take the genes for those, and then put them into your GE crop. It actually is a little bit like vaccinating, whereas when you put that gene into your test crop, what it blocks is the virus from being able to make that protein. So the virus can still infect the plant, but then it can't replicate because it can't make its own protein anymore. That's how that technology works. It's called RNAi, or silencing RNA. Yes?
So you're talking about doing this in small, in smaller areas than just based on viral changes, which is an interesting process. What is the average cost? Any idea what the average cost is of each time they choose a different gene and just, I know that's a huge question and.
Well,
Can you break that down in terms of creating the organism versus
I
the
will.
regulatory
Exactly.
cost?
The largest cost by far are the regulatory hurdles it takes, the testing in fact, in order to get it commercialized. The technology itself to change the genome with a very specific gene addition, or the new technology called CRISPRs may allow us to change the DNA within a plant without adding any DNA from abroad, quite cheap. So you can do it, you can probably do it for under $1 million. But the regulatory costs, it depends on where you are. If you're in Europe, the regulatory costs have gone up 5,000% since they started doing this in 1996. You can't get something passed in Europe, they just won't do it. Depends where you are. Brazil actually now deregulates GE crops faster than North America does. And soon we'll see, China's got 1,000 different genetically engineered crops sitting on the shelf, working their way through their regulatory system. 1,000 different varieties. There's only about 150 in the world right now. Yes?
I didn't think China would have a regulatory
No, I was just gonna say that.
Well,
regimen, but
they call it that.
that's just,
they call it that,
That's just
yes.
an observation.
But-
Just
but-
the guy that's gonna get killed if something goes wrong.
Yeah, the one that is demonized here is Atlantic salmon.
Yes.
And is it because Atlantic salmon is just one type of salmon and we have several types on the Pacific coast? 'Cause it seems that, for instance, when it comes to farming, they're using Atlantic salmon.
They do, because they're less aggressive. It's very difficult to farm Pacific salmon. They're such an aggressive fish that they kill each other
Oh,
in a confined environment. So it's very difficult. There's very few Pacific salmon that you can actually grow in captivity. So we grow Atlantic salmon. Now, there's also a very strong lobby from the people who have been fishing Pacific wild salmon for a long period of time. And they contribute a great deal of money to causes that would challenge Atlantic salmon farming. If you want to learn about the environmental impacts of Atlantic salmon farming on the West Coast, there are two documents I highly recommend you read. One is the Pacific Salmon Forum, and the second one is called the Cohen Commission. Both of those looked at decades of research.
Sorry, the which commission?
Cohen,
Cohen.
C-O-H-E-N, and the Pacific Salmon Forum. Both of those are available online. They're large documents, and both of them looked at multiple decades of research as to the environmental considerations for Atlantic salmon. And both of them came to the same conclusion. There's no smoking gun. All forms of agriculture have some impact. There's no free lunch. The trick is to get the maximum yield with the minimum impact. And aquaculture, as it's presently practiced, because we've improved dramatically since the early 80s when we first started farming salmon on the West Coast, the impact of present-day farming of Atlantic salmon has a minimal impact on the wild population. That's a consideration of both the Cohen Commission and the Pacific Salmon Forum. And don't take my word for it. Please go read those documents. Any other questions? Yes?
Just a quick one. I'd like you to comment on the use of random mutagenesis and ionizing radiation.
Oh, I mentioned that we have been changing the DNA of our food for a long period of time. For most of millennia, we did it by random mutations that just naturally occurred, and then we selected for them. That all changed in about the 1930s, when we became actively mutating the entire genome of our food, and then we just took whatever came out the other end. If we liked it, if it gave a redder tomato or a bigger strawberry, we went with it. So we mutated the entire genome of food crops, many, many different food crops, and then never tested them at all. That was a standard way of and it is still a way today of generating food crops. But if you add one or a couple genes, a known gene in a known location, know exactly how it's expressed, know exactly how it interacts with the environment, some people feel this is a big danger. Scientifically, it doesn't make much sense. And we've looked at decades of research, and we can't find the harm. We can find certain risks that are not unique to GE crops, but are found in all forms of agriculture. Agriculture has impact. There's no free lunch. But GE crop technology has not demonstrated any unique risks beyond the usual risks associated with other forms of breeding.
You're obviously very passionate about it. I appreciate hearing from you.
Yeah, from the level of questions here, I think everybody found that as fascinating as I did, and please join me in thanking Rob. That was great, and hopefully
Great. Quite happy to.
Thanks again, Rob.